We have a learning machine flash talk session. We have 5 speakers here, and we're going to talk about 5 different topics, or specifically 5 different papers. And the goal is to have approximately 5 minutes for each speaker, and then a few minutes for discussions. This is not a strict limit, so it can be a few more or a few less minutes as well. I'll stop the sharing, and Aleksis, you can take over the screen.
Okay, thanks. Yes, let's begin this flash talk with a new model which was recently proposed by DeepMind, which is called the Perciever. So it was published at ICML this year. So it's a general perception model with iterative attention. And I have drawn some stuff on top of this PDF on top here, which will hopefully motivate a little bit about this architecture. So it is a type of transformer architecture, which, as we all know, has become very popular in recent years. But there are some issues, and I will try to highlight it here. So if you take a transformer for, let's say, translation from English to French or something, you may have a sentence, I am fine, which has, in this case, m equals to 3 inputs. What you do is you feed them through some embedding and positional encoding. So what that gives you is essentially for each of the words, some representation, in this case, 4-dimensional for illustration, obviously higher in practice. What you then do is you would like to compute self-attention, so to say, and you compute queries, keys, and values. So I have illustrated it for the queries here, which will also give you something which has m rows. So that's the crucial parameter here. The m is the number of inputs. I will come back to the issue soon. And you would do something similar for the keys and values. And to compute this self-attention, you have essentially a computation between the queries and the keys. And I have highlighted in red this product, which is m times m dimensional. And this has worked well, in particular for NLP and so on, where m may oftentimes at least not be too large. So it's only 3 in this case, but sometimes it may be, I don't know, 1,000 or something like that. But people are also interested in starting to use these models for vision and so on. And if you would take an image of size 224 times 224, that would give you like 50,000, m equals to 50,000 if you would just stack that image. And so one of the solutions was this vision transformer, which has become popular recently, where they divide an image into patches to reduce the number of tokens or words, if you will. But this Perciever model circumvents this altogether and is actually able to, I will show the architecture. So in the bottom here of the architecture, you have actually, for example, an image, which is this 50,000 dimensional thing. And they work with that directly. And they can also use other types of modalities like sound or point clouds and so on. But let's stick to the vision example here. So to circumvent this dimensionality problem that I mentioned, they do some sort of thing where they actually have a latent array. So they don't do attention between the image and the image itself, so to say, but they use some sort of auxiliary thing, a latent array, which is m dimensional, where m is typically much smaller than m, as they say here in the caption. So for example, you have 50,000 for the image, but this n might just be like 500. They show that that works well. And then they do similar operations, just as in a transformer, but using this latent, which has smaller dimension. So in this way, they are able to actually process images as they are. And what they also do is that they show that it's often beneficial to feed the image at multiple places, not just at the beginning of this architecture, but actually feed it again a few times. And I've drawn some arrows to indicate some interpretations of what's going on here. So essentially, the first latent here it places some sort of generic attention on the image. But then later on, so that the queries later on in the pipeline are essentially informed by what it has seen so far. So the image comes at the very beginning, but that influences the query later on. That's what these arrows are supposed to show. So then the model may sort of put its attention on a different place and so on later on. So I think I've already talked for 5 minutes, but that's kind of the gist of it really. I could obviously talk more, but what do you say, Olof? Is this good enough?
Yeah, perhaps we have a couple of questions there.
Yeah. Go on.
So I'm thinking this sequentialness, is it could it be applied to a sequential nature in the data as well? Could you think of sort of processing video or
Yes.
audio with it?
Yes. So they actually show in the experiments. Well, actually, what they do is that they actually work with some videos, not full videos, because I mean, even though they say that they can work with high dimensional data, using a full video is still too big even for this one. But they work with small video snippets. And they actually feed the full video snippets, the same video snippet in every place, so to say. But they also try to, as you say, use different, I mean, kind of like a recurrent neural network to feed different temporal, in different temporal places. So that also works. I mean, this looks a little bit like an RNN, and actually it can be seen as a variant of an RNN, especially if you share the weights between these different attention and latent transformers.
And they do share the weights?
It depends. On some of the experiments, they show that it works. Essentially, you know, sharing weights makes it more parameter efficient. So if you don't have sufficient data to train with, it makes sense often to share them, they say, because to avoid overfitting and so on. I mean, the results in general show that this model is competitive with kind of these architectures that are specified for the different tasks. So you take vision, you have the ResNet or vision transformer and so on. And this one is sort of competitive with those. And it's competitive with kind of, in some sense, the leading architectures in the different modalities like audio and point cloud and so on. Obviously, they don't beat all of them, but just the fact that they are sort of up there with all of them using the same architecture for all of them is kind of impressive, I think.
Cool. Do we have some more questions for Aleksis? If not, then let's go to Martin.
I will give a brief talk on the paper Prototypical Networks for Fusion Learning. And I will begin by briefly explaining a little bit what fusion learning is. And in fusion learning, the goal is to learn, so to speak. And we want to fit a model which at test time can generalize to previously unseen classes and correctly classify these, giving just a limited set of examples of these classes during test time. And these examples are usually called the support set. So during test time, the support set is typically some examples of the positive class we're interested in and some examples of the negative class or classes. And yeah, we can stay at this picture, that's good. So for example, a problem we could have is that we have a folder of images. We give our model some images of dogs and some images not containing dogs, for example. And then we want the model to classify each image in the folder and tell us what images contains dogs. But this procedure is not uncommon to apply during training time as well. That is, during training, instead of having access to all of the training data, the model gets a random subset of the classes in the training set and some random examples of these as its support, and are then asked to classify what is called query images from these classes. So this paper addresses this problem with what they call prototypical networks. And the idea is centered around that there exists an embedding in which points cluster around a single prototype representation for each class. So this prototypical network consists of a nonlinear mapping from the input data into an embedding space. And we can see this embedding space as the rectangle in the figure 1 here. And this in the paper is done by CNN blocks. They try their approach on images, but this method has proved useful for other domains as well, such as sound event detection. So the next step in this model is to create the prototypes for classes in the support set. And this is done by averaging the embedded support points belonging to this class. And this again, we can see in figure 1. We have 3 colors here, orange, green, and blue. And we have 5 support examples in the class blue, for example. And then we end up with prototype C3, which is the average of the embedded points. And then we have this query image X, which we want to classify. And we also put this into the embedding space. And then we classify this query point by selecting the prototype, which is nearest to it in the embedding space. For this figure, it is prototype C2, or the orange class. I think this figure visualizes their idea quite well. So I think this idea is quite elegant, and they achieve good results compared to other few-shot learning approaches of the time when this paper was published. And it was published in 2017. I think, yeah, there are some results, yes. And I think there are more results on page 6. So yeah, this idea really took hold, and it has, in my understanding, more or less become a staple in few-shot learning, whether you're working with sound or images. And since the publication of this paper, a lot of variations of this idea have been published as well, improvement of this network, so to speak. And if this sounds interesting to you, I can highly recommend reading this paper. That was my talk. Thank you.
Thank you, Martin. Do we have some questions for Martin? Is this, I suppose that this is evaluated on image dataset?
Yeah. This paper works on image datasets, the mini image and Omniglot. Yeah.
Omniglot, yeah. So do you know if there are any follow-ups on other kinds of data?
I mean, I know people have used this idea of prototypical networks, for example, sound event detection, with quite good results there as well.
Cool. Any more questions?
Yes, I was wondering, Martin, have they done any comparison for how many support samples they need for each class, and how that affects the few-shot learning? Yeah,
I think they have. If we go to page 6, I think they have a table of results. For example, here they have 1 shot, 5 shots. Oh, this was not a page. This is it. Yeah. Sorry. They have a table on page 6 where they show accuracies for 1 shot and 5 shots. I don't know if they have any data on different ways, but yeah. Does that answer your question, or?
Yes, thank you.
So they seem to make significant improvements on both 1 and 5.
Yeah, and increasing the support set, or increasing the size of the support set greatly increases the performance compared to just having 1 example per class, which is kind of natural, I suppose.
Any more questions? Okay, thank you, Martin.
Thank you.
Next speaker is Edvin.
The name of the paper that I will talk about is called Exploiting Shared Representations for Personalized Federated Learning. And before I go into that, I will briefly just go over what federated learning is for those of you who are not familiar with it. So federated learning is a framework developed by Google in 2016 for distributed machine learning, more specifically for decentralized machine learning, where data is decentralized in many different clients, for example, mobile phones. And the goal of federated learning is to learn one global model by decentralizing the data between clients and training models locally, sending the model parameters to a central server where they are aggregated, but doing all the computational, the backprop basically on each local client. A problem with this framework is that when data is very non-ID, or basically when client data is very different from each other, doing a naive averaging of the weights in the server, the model parameters won't give a good global model. So what this paper does is that they develop an algorithm basically to solve this problem. And if we scroll down, I think the most important part is section 3, FedRep algorithm. Exactly. So they have 2 steps here. They have the client update and the server update. So in regular federated learning, what you do is you train your model locally on the data that you have on your local mobile phone, for example, and then you send your model to the central server, and you do this with all the models, where they are aggregated into one global model, which is then sent out to all clients. And this is one communication round, and then this is repeated until convergence. However, in this paper, instead of training the whole model and sending the whole model to the server, they train only, basically they have shared representations between each client, but they have a specific head for every client, which they train uniquely for every client, but the representations are shared. And they do this by first training, basically giving a model, excluding the head. Given those parameters, they train only the head for many, many local epochs locally. So they get a specialized head on each client, specialized for the task at that client. What they do after that is what they call the server update. So then they fix the head on each client, but they update the representations, or basically the rest of the model, excluding the head. And then they send this to the central server. So basically it's exactly the same thing as regular federated learning, just that they freeze the last layer and communicate only everything else. And they actually get pretty good results doing this. So by doing this, you can imagine that each client is specialized to its own task, but they still learn some common representations that are useful for all clients. If we go to the large table of results, table 1, I want to stress one specific thing here. Of course, it's their paper and it's published in ICML, and it outperforms every baseline that they test, which are many different types of personalization methods in federated learning, which they beat them all. However, I want you to compare their results, which is the last row, to the federated averaging plus fine-tuned FT, this second row. And you can see that FT stands for fine-tuning, and you can see that their results are very similar to fine-tuning. They don't give any standard deviations here, so it's hard to draw any statistical conclusions from this. But what I think is interesting from this paper is how efficient just fine-tuning is. Basically, if you do federated learning get a global model, and then in the end, you just fine tune it on every client, you will get a very good model with minimal communication cost, basically, or you don't have to communicate anything more than regular federated learning. Those, I would say, are the main findings of this paper.
And that also mirrors some findings that you've made in your experiments.
Exactly.
I actually...
Beating fine-tuning is hard in federated learning.
I actually think that some of these, when it's bold-faced, some of the times I doubt that this is statistically significant.
It would be interesting to see more results on that. They have some theoretical reasoning about their proposed method here, but I haven't digged into those proofs. But yeah, and also they don't mention anything about hyperparameters. So basically, a question I have here is how sensitive is their method to hyperparameters compared to fine-tuning as well? My intuition says that if you do that thoroughly, perhaps these differences would go away. However, their method is very similar to fine-tuning. If you just think about what they are doing, they are basically fine-tuning ahead of their model in every iteration and learning a shared representation. And then this you could do on different layers. They choose to only freeze the head here, but you could imagine that you freeze different depths of the model. And you can imagine doing this differently for different clusters of clients as well, if you identify clusters in your federation.
Did we have a question?
Yeah, this is okay here. Yeah, that was kind of close to my question. When you do the federated averaging with fine tuning, do you fine tune typically the whole model then, or just the head?
Yes, so that you can test to do whatever you want, basically. But the most common thing, or the first naive thing to do, is just train a model in federated learning, and then when you're done, fine tune the whole model on each client. But you could try to only fine tune the last part of the model, like the head or the top N layers or something, because probably those first layers you won't need to fine tune, because there you often have the overall high level representations that you need. But whereas as close to the head as possible is probably where the client task specific things happen. But I think in this paper they fine tune the whole model in their fine tuning baseline.
Okay, thank you.
Hi, Edvin. I was curious about how does that deal with, say, imbalanced or skewed data that you might have in different nodes where you train the model?
It's a good question. I omitted that, but actually that is what these numbers are reported on. So you see, for example, the first column there, Cypher 10, I think the first number is number of clients and the other one is number of classes per client. So you see what happens if you only have two classes per client and only 5 classes per client for 100 clients. So basically that's the problem they tried to solve. What happens if we have a label skew? So some clients only see 2 classes, and that's why you need personalization, because you want to be as good as on those 2 classes as possible. And you see you get very high scores. When you have only 2 clients, you can see that only doing local training yields high accuracy because, well, it becomes a binary classification task, basically. So they get 89.79% accuracy, which is actually better than doing FedRep.
So if I'm reading this correctly, it's 100 different clients, and each of these clients have 2 classes.
2 classes from Cypher 10, exactly.
So how would they deal with, say, one client has 5 classes, another one has 1 class, and another one has 50.
I don't think they look at that in this paper, but that would be, you could definitely look at that as well. I would say what they are doing here is the one extreme point of what you're proposing, but you could have different number of data points on clients, and you could have different number of labels, as you say. You could also imagine having different input features of different clients as well. So the statistical properties could be different, but in this paper they only limit themselves to look at label differences and these very simple experiments.
Thank you.
Our next speaker is Ebba.
All right, so I'm going to talk about MD-GAN, a multi-discriminator generative adversarial network for distributed datasets. And in short, one can say that this is the first paper to address generative adversarial networks, or GANs, in a federated setting. And since we just heard about how federated learning works, I will skip that part and go into a brief description of what a GAN is. So a GAN is a deep learning model with the purpose to generate realistic data. And the model consists of 2 neural networks. We have the generator and we have the discriminator. And these 2 are connected to each other. It's the generator's purpose to generate realistic data, and the discriminator will learn to distinguish between real data and data that comes from the generator. And it's also the output of the discriminator that will direct the learning of the entire model, and eventually, and hopefully, we have a discriminator that can't tell the difference between real and generated data anymore. So this paper considers such a model, a GAN, and how it can be adapted to the federated setting. And they have 2 different approaches to do this, which I've demonstrated in a figure here. So in this right picture, you see what they call an AFL GAN. And this is basically a direct adaptation of federated learning to a GAN, where both the generator and discriminators are placed on the workers or the clients. And we have one version on a central server as well. And after a fixed number of epochs at the workers, parameters of the worker networks are averaged at the central server and also sent back to the clients to update the local networks. On the left here, on the other hand, you see the proposed MD-GAN. And in this version, it's only the discriminators that are placed on the clients, and the generator only exists at central server. So for the MD-GAN, generated data is produced at the server and also sent to the workers for the training. And then the clients train their separate discriminators and also sends back a loss for a batch of generated data, which is used to update the central generator. There's also the additional feature of swapping discriminators between clients. And this is done to counteract problems such as overfitting or small data sets, which might be the case when the data is distributed over many clients. And the main idea behind this MD-GAN is to maintain a federated setting where data is kept private or local, and also decreasing the workload on the clients, since GANs can be quite computationally heavy, and therefore place half of the computation, and that is the update of the generator on the server instead. They perform some experiments on both of these networks, and they also compare it to a baseline GAN or a standalone GON. We have the main results in this figure. So they use both inception score in the top row, where a high number is good, and they use threshold inception distance in the bottom row, where a low number is good. We have the standalone GON in black, the FL GON in red, and the MD GON in blue. And as you can see, the MD GON performs basically on par with the standalone GON for the architectures and the data sets that they use for these experiments. They show later in the paper that there are some problems with the MD GON when you go to more complex data sets, so when you investigate eventual crashes of the workers. But overall, this is a quite interesting starting point for the research topic of GONs in a federated setting, and has sparked further research on the topic after this paper. And that was all I had.
Thank you, Ebba. They call it standalone GON. So the standalone GON and the federated GON, what is what data do they use?
So in these experiments here, they have the MNIST dataset, which is an image dataset of numbers, and the Cypher10, which is also images, but of 10 different classes of various objects.
And is this distributed along the client?
Sorry?
Is the data distributed among the client?
It's identically, it's IID distributed, if that was your question.
Yes, and
yeah.
Standalone GON has the whole data set.
Okay, exactly. So that is also something that has been not done in this paper, but has been investigated in papers after this, the non-IID setting, which might be more interesting because it's more similar to the real life applications.
Cool. Do we have some more?
Do they mention anything in terms of if this is actually keeping the privacy concerns or privacy preserving concerns? Because it's quite easy to assume that the distributed discriminators will tend to overfit on the local data. So if you're sharing the discriminator weights between clients, I would assume there's a lot of information leakage between clients.
Yeah, that is not discussed a lot in this paper. I know that there's other papers focus more on that, but I don't think they consider that at all in this paper.
Okay, all right. Thank you.
Okay. Thank you, Ebba. So I got a bit envious of everyone reading federated learning papers, so I also took a federated learning paper. I picked this mostly because I think the combination of federated learning and unsupervised learning is an interesting intersection, both for some challenges that are there and also for sort of the naturalness of the application. You can easily imagine that you have large amounts of unannotated data on distributed clients, and if you can leverage that for a model, that could have some nice applications. So here they're looking into the Sinclair model, and well, there has been a couple papers on unsupervised learning and federated learning before, and they have mostly just taking one technique for unsupervised and then just federated it. So one of them did this specifically with a Sinclair paper, a simpler idea, where you do some contrasted learning for training representations for images. They do this here as well, but then they identify a couple of these issues that can happen, and that is specifically when you have non-IID data. So in figure 1 here, you see under A, what they call inconsistency of representation spaces, and that's typically one thing that can happen if you have labels on one of the clients and you don't have them on another client, and so one model can put a dog where another model put a plane in the same part of the representation space. Another thing is what they call misalignment of representations, and this is something that they actually measure in with an angle between the representation vectors. And so they go ahead and propose some solutions to this. I'm not going to go into detail about what they do. It's a bit cumbersome and it's a bit arbitrary. And in the end, I don't really think they benefit that much from it, as you'll see in some tables. But they propose this algorithm, and as you can see in A here, it's more or less a typical federated scenario, but except for the local models that you send to the server and back, you also send something they call the local dictionary, which is representations for the local data using a global model. And this they use to sort of align these the representations in the setup that they have in the middle section of this figure, the B here. They also keep a history of these local representations, and they have an ensemble strategy for sort of, in my impression, they seem to sort of regularize or make the updates a bit slower. So here they compare t-SNEs of representation with what they call vanilla here, which is exactly the simpler strategy, just federated, and they don't seem to find the clusters at all, I suppose. But then again, I'm not sure it's that much better in the B here, which is the proposed model. And I suppose they claim that most of the ones here, I'm not sure it's that clear on the screen, but most of the ones are in the B area here, and most of the zeros are in the A area here. And to my naked eye, the X's are spread all over the place, but they sort of claim that they're mostly towards the C, and perhaps there's a tendency towards that. And perhaps there's more of a tendency towards that in their B here than compared to the vanilla A. So perhaps these ideas do make some difference, and also in this figure 4, here they call it Fed simpler and not vanilla anymore, but this is the vanilla. Where they measure the angles between representations encoded by 2 different models, and then they compare this to the proposed model and see that they get lower angles comparing the same data with 2 different local models with their approach. And so what they call non-IID data here is strictly dividing the CIFAR-10 data set along between 5 different clients, and they have exactly 2 labels on each such client. And to me, the experiments are very limited. They're also very unclear about hyperparameters. So there may surely be a case where where they don't really beat the baselines, but they don't show it. I would imagine that if you update your models more often, or if you have a little bit of an overlap between the distributions of the data sets, here they have no overlap between in the non-IID setting. The baseline methods may work much better. And if you look at the tables, well, it's not an extreme difference, I think. Okay, some of the scores are a bit better, but I think I have a difficulty of determining whether that is a major contribution here. But I think the idea is great, and I think we're going to see a lot more along the lines of unsupervised learning and federated learning. This is, by the way, an unpublished archive paper. Yeah.
So a question. So this dictionary, what does that actually mean?
Yeah, that's a good question. The dictionary is they store a number of representations for their local data, which is computed not with a local model, but with a global model. And in that case, I think it's the federated model. But in another case, they have the alignment model, which is actually trained on central data. So that's actually something that I forgot about. And that's something that makes this approach a bit more, I don't know, cumbersome and perhaps not that desirable, because you actually need to have a global data set as well, which they use to train an alignment model, which is distributed around to the clients, which is then used for some regularization.
So what I'm thinking about is that in some weird conceited way, it feels like it's almost related to Léon Botteau's work, which we had talked about before, this invariant risk minimization. So kind of trying to reduce these spurious correlations between different data sets. So colored MNIST stuff. And I mean, at least when I think about these things in terms of federated learning, in some sense, the local clients do have potentially a spurious correlation to their local data set. So actually having that distributional difference between the data sets, what I'm thinking is maybe that's a good thing. Maybe we can actually use it to kind of combat these spurious correlations and actually get a more robust model.
Use what?
Sorry?
We can actually use what?
I mean, if we look at it as different data sets in different clients, so this distributional difference between the central and the local, that distributional difference represents a spurious correlation. That's the assumption. So if we can use that difference to actually train a more robust central model rather than just averaging it or compensating for it.
Yeah, so I think you're right, and I think they're after this, and I think the idea is not that crazy.
Yeah. So what I'm thinking is that I mean, there should be some relation to this invariant risk minimization from Botteau. But I think, yeah. I mean, at the same time, it's quite weird because it's still conceptually within the same data set. It's just that it happens to be different batches in different clients in this particular case. So
it is a synthetic setup of the non-IID-ness, but that is also sort of how you do in the field. When you have the label skewness, you usually do it in this way or some variant of it.
Anyway, I think I mean it's interesting in the sense that it kind of relates to this causal reasoning in terms of data sets. But yeah, thank you.
Thank you. Thank you all for listening. Next week, we will have a talk by Nishat Mola, who is our RISE colleague and working in the intersection between cybersecurity and machine learning. So welcome back next Thursday, same time.
Everyone.
Thank you.
Thank you very much.